Please welcome Suzanne Smith, Chair of the Honors and Awards Committee, to the stage.
Thank you. Well, good afternoon, everyone. Welcome to the AIAA Dryden Lecture and Research. As he said, my name is Suzanne Smith, and I'm the chair of the AIAA Honors and Awards Committee. The Dryden Lectureship is one of our most prestigious lectureships bestowed by the Institute. This award emphasizes the importance of basic research in advancing aeronautics and astronautics. Since the inaugural lecture in 1961, it's been a catalyst for sharing research advancements and knowledge with our wider community. This premier lecture is named in honor of Dr. Hugh L. Dryden. He was a renowned aerospace leader. He was the director of the National Advisory Committee for Aeronautics, NACA, which of course was the precursor for NASA. He was also the first deputy administrator of NASA when the agency was created in 1958. Our 2026 AIAA Dryden Lecture and Research is awarded to an international authority on long-sought capability in aeronautics and significant turbulent boundary layer net skin friction drag reduction, Dr. Thomas C. Cork. His lecture is titled Active Drag Reduction with Net Power Savings in Turbulent Boundary Layers, Physics and Scaling. Please allow me to introduce you to him. He's the Clark Chair Professor of Engineering at the University of Notre Dame, and he's the founding director of the Notre Dame Institute for Flow Physics and Control, or FLOPAC. He is the third director of the Notre Dame Hessert Laboratory for Aerospace Research, and he currently serves as the director of their Hypersonic Systems Initiative. Dr. Cork is an AIAA Fellow. He's founding chair of our Institute's brand new technical committee on fluid instabilities and transition. He's also a fellow of the American Physical Society and the American Society of Mechanical Engineers. And in today's lecture, Dr. Cork is going to examine the realization of a long-sought capability in aeronautics, namely significant turbulent boundary layer net skin friction drag reduction. Laminar flow control can be applied for skin friction reduction on wings, tails, and engines. However, for sizable transports and many other applications, significant turbulent boundary layer drag reduction has long been sought. So we're looking forward to hearing from Dr. Cork. And if time allows, we'll have a question and answer session at the end. And so please refer to the QR code that's going to appear on the screen up here to submit and vote up questions. Now, please join me in welcoming our distinguished lecturer for the 2026 Dryden Lecture and Research, Dr. Thomas Cork, with his lecture, Active Drag Reduction with Net Power Savings in Turbulent Boundary Layers, Physics and Scaling. All right.
Thank you. Thank you very much.
Thanks.
Thank you. Let's see here. I'm going to there we go. So to start out, I want to acknowledge that this work. So what I'm going to present to you is really the collective work of two of my PhD students, one Alan Duong, who graduated in 2020, and then Andrew Myers, who completed in 2023, as well as the collaboration of my colleague, Professor Flint Thomas. At the end of this talk, I will have a list of publications, and you'll see their names are prominent in those lists of publications. The initial work was supported by NASA and DARPA, and then it's currently being supported by the Air Force PACER program as well as DARPA. So let's put this in context. Skin friction constitutes approximately 50% of the drag at cruise of an aircraft from business to long-haul aircraft. A 10% reduction in skin friction would result in about a 9% fuel savings for 4,000 nautical mile aircraft. For a supersonic aircraft, it's actually even more important. Fuel is approximately half the gross weight of a supersonic aircraft, and fuel reserves for landing exigencies are on the order of the takeoff of the payload weight. So a 1% reduction in total skin friction on a supersonic aircraft would result in 5 to 10% increase in payload. A single drag count would reduce the gross weight of a supersonic aircraft by 4,000 pounds and save 7,500 pounds of fuel. This is data that was compiled by Dennis Bushnell. So some background. The importance and possibility of viscous drag reduction were first seriously identified in the 1930s. In the 1980s, turbulent skin friction reduction was considered to be a major barrier problem. The pursuit has been a catalyst for development of passive and active flow control devices to reduce skin friction. And our accumulation of knowledge over the last 40 years has really focused on two approaches. Those are called and denoted as what's called top-down and bottom-up. So top-down is where the outer large-scale structures trigger near-wall turbulence production. So your left plot there, the left plot shows a device that actually I worked on in my PhD, in which we placed parallel plates, somewhat like a two-dimensional honeycomb, within the boundary layer, relatively high up in the boundary layer, and they were designed to suppress the large-scale motions. And you can see, comparing the left photograph to the right photograph, that they were successful. As a result, the skin friction was reduced by about 20%. In addition to that, there was also about a same or comparable reduction in the streamwise velocity fluctuations. And there was a reduction in the turbulence production mechanism, which we're going to just call bursting, by about 17%. Now, the bottom-up approach is on the right side, and this is viewed as a near-wall turbulence generation in an autonomous cycle. Now, this was largely viewed based on some flow visualization that Professor Klein did in 1967 at Stanford, in which they visualized the flow field in the near-wall region of a turbulent boundary layer. And what they saw was that the particles formed into these kind of streaks. And in fact, these are referred to as the streaky structure, okay? Now, clearly these streaks, the formation of these streaks are a result of coherent streamwise vorticity, okay? And that's a key thing. Now, Klein and his group found that the span-wise spacing of these streaks scaled with the inner wall or viscous variables in the boundary layer, giving a lambda plus of 100. They also found that the breakup of these streaks scaled with the shear velocity or skin friction of the boundary layer. And that's a key result that I'm going to expand on. So in terms of devices that are designed or maybe indicated to control this bottom-up process, one is riblets, which I think most of you know about. These are a passive device, and they will reduce the skin friction by about 7%. And then another one, which is an active approach, is a span-wise oscillating wall, which is very effective, would reduce the skin friction or viscous drag by 40%. However, the power that it took to oscillate the wall far outstripped the power you would get back from reducing the drag. So it's not a practical approach. However, it does point to the mechanism. So what I'm going to present to you is our approach in taking a bottom-up effect, a bottom-up approach, okay? And so the left plot is again the image from Klein. And the data underneath that plot is actually measurements that they did, which is measuring the streamwise mean velocity in the span-wise direction underneath that, that visualization. And what we see is that there is a modulation of the mean velocity, which is a result of this pumping action of the streamwise vortices. Okay? Now, a metric of that mean flow distortion is the wall normal vorticity, omega y. So Chopin and Hussein in 2002 introduced a criteria for something they called streak transient growth, in which the wall normal velocity, wall normal vorticity, omega y, was a critical parameter. And so the basis of control that they recommended was controlling omega y. So I've taken and made kind of a schematic of this streak transient growth, which is shown in the bottom right of the plot. And so it starts out at the top, generation of the coherent streamwise vorticity, which we see as the result of which is this streak structure in the visualization. That streamwise vorticity then results in a spanwise mean flow distortion and the generation of omega y. When omega y reaches a critical value at the bottom of this cycle, then we have the generation of turbulence production through an instability growth. And then the cycle just repeats. So our approach to reducing the viscous drag is to break that cycle. Okay? And so that's what this is about. How do we break the cycle? Well, the way we're breaking the cycle is to introduce a span-wise, steady velocity component in the near wall region of the boundary layer. The idea is to take those variations and smooth them out. Okay? So from an instability point of view, what we're doing is to modify the basic flow. So we make it more stable. Okay? So how do we generate this span-wise velocity component? Well, we're going to do this with plasma actuators. Some of you might know me that I've been working with plasma actuators for probably 40 years now. This particular plasma actuator is one we call a pulse DC. And so the plasma actuator consists of a surface electrode that is laying on top of a dielectric layer, which then covers a lower electrode, which is underneath the dielectric layer. Now, electrically, that configuration is a capacitor. And so the capacitor will not pass a DC current. What we supply is a DC load, a DC source to both electrodes, the exposed electrode and the cover electrode. And then we pulse very short pulses, which with a solid state switch that will cause current to run between the exposed and cover electrode. That's the only time when power is consumed in this process. The ionization that occurs in this process, along with the electric field, results in a body force that pushes the air to the side. And so on the upper left plot, you see kind of a configuration. You see the blue lines, that's the plasma, the ionized air, and then that generates the span-wise velocity component. Now, the power we put in is incredibly small. It must be small because if we want this to be practical, the amount of drag reduction we get and convert it to power must be more than the power we put into the actuator. And in fact, it is. So the initial experiments were done in a Notre Dame Mach 0.6 wind tunnel. The boundary layer was developed on the floor of the tunnel. On the floor of the tunnel, we have a floating element. It's a 9-inch by 9-inch element that's mounted on air bearings, and the force is measured with a load cell. We have interchangeable load cells to increase the resolution and accuracy. You can see on the right that we located the actuator array onto the load cell. You can see the electrodes on this case. A key parameter that I'll point out is the spacing between the electrodes. If you want to consider this to be a source of blowing, it's the space between the blowing sources, okay? In this case, we define that as delta Z in this particular example. From a nomenclature, Z will always be span-wise, X will always be stream-wise, Y will always be wall normal, okay? Now, in this case, we ran 4 different designs with different delta Z's, different voltages. The Reynolds number based on X ranged from 2.8 million to 8.1 million, and RE theta, which is really a more important metric in turbulent boundary layers, was 4,700 to 10,386. These are healthy turbulent boundary layers, canonical zero pressure gradient boundary layers. The maximum power that we put into this was 14 milliwatts per square meter. I have a little arrow there that shows the power lead. You probably can't even see that. It's literally a thread, okay? And it's a thread because we didn't want it to generate drag itself, right? Okay, so it turns out that the amount of span-wise blowing that we would put in was order of the friction velocity u tau. So that's an important consideration. The first results we got are shown here. Let's focus on the left plot. The left plot and the curves which are on the right side of the left plot, that is our data. And what we've done is we're plotting the ratio of the friction velocity, which square of that would be the drag reduction, versus the spacing in wall units of the blowing sources, okay, or the electrodes of the plasma actuator. And what we can see is for different voltages that the dominant scaling is in fact the spacing, the span-wise spacing of the blowing source, okay? At the lowest, where lambda z plus is 1,000, that's giving us close to 80% viscous drag reduction, okay? Now, on the upper scale there, if you divide the numbers on the bottom scale to the upper scale, we've just divided it by 100, and now we can say how many streaks that corresponds to. So at the largest drag reduction, that corresponds to about 10 streaks, okay? Now, the other set of data that is not as steep is from an experiment that was recently done by Wei and Zhao. And this is fortuitous because what they did is they almost exactly repeated our experimental setup. But they ran it at a much lower Reynolds number. But that was fortuitous for us because it then allowed us to also scale with Reynolds number, okay? I also should point out that the change in the friction velocity was logarithmic in the spacing, and that's a key thing. So now if we take the 2 sets of data, our data and the data from Wei and Zhao, knowing that there's a difference in Reynolds number, we can now see the scaling with Reynolds number as well as spacing, and that's the right plot. And you can see we've collapsed all the data from 2 different independent experiments. The scaling is important because we want to take this information and we want to actually bring it to full scale. And to do that, we have to understand how it scales. Okay. In addition, taking the Wei and Zhao data, they plotted, and we overplotted their data, which is, again, the ratio of the friction velocity in the nominal boundary layer to that with the drag reduction. And the key here is that W is, of course, the span-wise velocity component. This has been normalized by inner wall variables, so it's W plus. And we see that it falls linearly with W plus Reynolds number tau. Now, they use a much lower Reynolds number range than we did, and so but what we did is we found that we could place our data at the lower Reynolds number right on their curves. So again, what we've done is we've been able to independently, using the proper normalization, overlap our experiment to their experiment. That sets the scaling. Now, we wanted to check the scaling, and so we did another experiment in which we put this actuator array on the upper surface of an airfoil. This is a NACA airfoil with a chord length of half a meter. It's a serious airfoil. It spanned the full height of the Mach 0.6 tunnel, and the Reynolds number based on chord was from 3.4 to 5.7 million. Okay. It's also in a region of somewhat average pressure gradient. Now, we designed this to run at 3 Reynolds numbers, or range from Mach 0.3 to Mach 0.5. Those previous measurements, the highest Mach number was 0.2. So this is extending the range in terms of Mach number or velocity, as well as checking the scaling. And in the case of the scaling, we designed this so that it would produce a drag reduction predicted of 40%. So the result is shown here. In the upper right plot, you see that across the Mach number, we got a 44% drag reduction from Mach 0.3 up to Mach 0.5. Another result of this is the plot in the bottom right, which shows the scaling. We would predict, because the requirement of the span-wise velocity is order of u tau, we would predict that the net power savings would scale as roughly close to Mach number squared. And in fact, what we see is that it scales, in our experiment at least, as Mach number to 3.5 power. The implication of this is that the faster you go, the better return you get in terms of the net power savings. Okay. So for example, at Mach 0.5, we got an 1,100% net power savings. Okay. So having this tool of being able to reduce the viscous drag, we now wanted to use it to understand characteristics of turbulent boundary layers. So then we devised this experiment here, in which we use an artificially thickened boundary layer to give us good spatial scaling. And then we again have an actuator array which is on the floating element. But we used 2 hot wires. One hot wire, which was an X wire, was fixed in space. And the other hot wire that could either measure U and V component or U and W component was allowed to move in 3D space. These hot wires were located slightly downstream of the actuator array. This was an artificially thickened boundary layer, but it was highly two-dimensional. The left plot shows mean velocity profiles at different span-wise locations across the whole platen. The right plot shows the wall normal variation in the streamwise, wall normal, and span-wise velocity fluctuations against a zero pressure gradient reference, which is from Klebanoff in 1954. So this is a well-behaved boundary layer. We then adjusted the conditions, that is the voltage, to the actuator array to find the minimum or the maximum drag reduction. In this case, it was 62%. You'll notice there's 2 sets of points on here. That's 2 experiments that were separated by 2 years. Okay? And so you can see the repeatability of this. When we lower the viscous drag, we see there's a lowering of all 3 velocity fluctuations almost completely across the boundary layer. In addition, we see a lowering of the UV and UW Reynolds stresses. The UV Reynolds stress can be used to calculate the turbulence production, in which case we find the turbulence production was reduced by 66%, very close to what the drag reduction was. Okay. Now, we can also measure the frequency of the breakup of this streak structure, just the way Klein did. So here we're going to use a technique which is called a variable interval time average, or VITA, that was developed in 1976. And what we're plotting here are the change in the number of events, this burst events or turbulence production events, as a function of change in Reynolds number. We have a few spurious data points on here that seem to come up. Nonetheless, what we see is that the frequency of these turbulence production events is linearly dependent on the change in the drag. Okay, and again, two different experiments, Duong and Myers. Now for check, I also put the value on here for my Lebu experiments done in 1981, and you can see, although that is really a point, not a bar, that it falls on that straight line. Well, this is of course exactly the result that Klein found in 1969. That's a key thing. So if we lower the wall normal vorticity, we lower the viscosity, the viscous drag, and then we also then lower the turbulence production. In addition, that the frequency of these events is lower, the intensity of the events is also lower. Here we're showing UV Reynolds stress and UW Reynolds stress, and the reduction from baseline to the drag-reduced boundary layer is evident. So now we wanted to do kind of an ensemble reconstruction. What did the structures look like in this drag-reduced boundary layer? So now what we did is we used this VITA technique as a trigger in order to be able to obtain an ensemble average visualization of the flow field, and in this case, the vortical structures in the 3D space. Okay? So now in doing that, we had to make sure that the features were correlated from the point of detection, which didn't move, to that spanwise or 3D position. And so the right plot here just shows us that we feel we can ensemble average over the space, which is about 400 wall units. So everything I'm going to present will all be limited to 400 wall units. Now, as I pointed out, the omega y is the critical parameter in the control. So what you see plotted here is the omega y in the spanwise and streamwise direction with color contours. And so the color contours levels are identical in these two plots. The upper plot is for the baseline boundary layer. The bottom plot is for the drag-reduced boundary layer, 62% drag-reduced boundary layer. I think it's evident by eye that we've reduced the omega y, which again is the critical parameter. In fact, if we average over that space, we find that we've reduced omega y by 58%. Now, the source of the omega y is, of course, the streamwise vorticity components. So now we're looking at the streamwise vorticity, omega x, again, looking down at the boundary layer, so this is an x plus, y plus frame. And for scale, I've also put Klein's image. That's the same scale as the contours. And so, again, if you look by eye, you can see that it's fairly clear that we've reduced the strength of omega x. In addition, we've also reduced the extent of the stretching, if you want, or coherence of these vortical structures. We also see that in the baseline boundary layer, the spacing between these is lambda plus of 100. And in fact, in the lower viscous drag, where U tau is lower, which is used in scaling lambda plus, we see that the lambda plus was preserved even when we lowered the viscous drag. To get a better idea of this, and let me back this up a second, we're going to do a cut through x plus of 0, and now show the plane which will be y, wall normal, z. Because this will then show, this is basically a cross-cut through the coherent streamwise vorticity. And so the top plot, again, is the baseline. The bottom plot is the viscous drag reduced by 62%. And you now clearly see that we've reduced the strength of the streamwise vorticity. one of the things we did, so I showed that the streamwise velocity fluctuations was correlated with the viscous drag reduction. So one of the things we did is we took a hot wire and we ran it over the plasma actuator array. And so the plasma actuator array extent is that box that says actuator streamwise extent. And then you can follow that down as a vertical dashed line. Now what we see, in fact, is that the response to the boundary layer is not immediate. It's not immediate. So the flow is going from left to right. And you see the streamwise velocity fluctuations, which are correlated with the viscous drag, is lagging in space. Okay? In fact, if your eye is good, you'll also see that there actually was a small upstream effect of the actuator array. So this led us to now think about what is the persistence of the drag reduction. Now what we'd like to do, we would have liked to have extended the test section so we could measure downstream, but we didn't have that length. So what we did is we in fact then turned the actuator on, then turned it off while still taking data, to then monitor how this relaxed back from the 62% drag reduction to the nominal boundary layer. Okay? And so the time that it was on was 10 seconds, which was long enough for it to have reached steady state, and then 20 seconds after that to allow it to come back to its nominal condition. Okay? In that, we were always monitoring the viscous drag, and so the viscous drag that was instantaneously changing is used in the normalization for T+. So here's a first result, and I have to say I noticed this just today. The title on this is not streamwise velocity fluctuations. This is the streamwise viscous wall shear velocity U tau. And so here we're looking at the ratio of U tau with the actuator on to off. The actuator turns on at turns off at T plus equals 0. And we're seeing then the rise back to the nominal U tau, okay? And we see in this case that it took about 4,000 T plus units to do that, okay? That's pretty key because Chopin and Hussein estimated it would probably be about that much. Also, we can look at the mean velocity profile, in this case looking at particularly focusing on the log layer. And so in the case of the 62% drag reduction, we're at the top curve in the log layer. Two things you notice. One is there's a bigger offset, okay, and that's because the boundary layer is thickened as a result of the drag reduction. In addition, we see that the slope is changed. So the Kármán coefficient is in fact changing as we reduce the drag. So in case it's not evident, the Kármán constant is not constant. Okay. A metric of these mean profiles is something called the Y plus center. Okay, and that's something that was discussed in the paper by Mathis AL in 2009. So we're plotting the Y plus center, again as a function of T plus, and again we see that this reaches equilibrium back to the nominal boundary layer in 4,000 T pluses. Okay. Next we look at now the recovery of the velocity fluctuation. So we're seeing all three velocity fluctuations, U, V, and W. And what's apparent is that the U component, which is the triangles, is recovering faster than the V and W velocity fluctuations. To see that better, we put a curve through those points and then now plotted the slope. And so clearly you can see the slope, the U RMS slope, is faster recovering than the V and W RMS components. Well, that actually is quite consistent because if you look at the bottom bullet, the turbulence production in a boundary layer transfers energy directly to the streamwise component, the U component, where the V and W components depend on the pressure strain rate term to transfer the energy from the streamwise component. So that's the physics of it, and this just is quantifying the physics of why the V and W fluctuations lag behind the U. Here is a final composite. And so here I'm showing the combination of omega y, which is the critical control parameter, the veta, which is the measure of the frequency of the turbulence production, and then the shear at the wall, tau at the wall. And so what we see here is a sequence. You can see that what recovers first is the omega y. Next comes the turbulence production. Next comes the shear at the wall. And so what you can now see that if you can cut off that connection between omega y, then you can cut off the turbulence production, you can cut off the growth in the wall shear. Okay. So now I'm going to summarize. So there's a consistent, repeatable reduction in the turbulent boundary layer, viscous drag based on applying a small, order u tau, steady span-wise velocity component within the boundary layer, and particularly within the sublayer, designed to interrupt the turbulence production mechanism. Using the pulse plasma actuators, we found a net power savings of 1,100% at Mach 0.5, and a scaling which says that the higher the Mach number, higher the speed, the more you get back in terms of the power you save. That's key because we believe that this method is completely applicable to supersonic boundary layers and potentially hypersonic boundary layers. In terms of the drag reduction, there was a 73% drag reduction efficiency. So if we kind of look at a thermodynamic efficiency of the actuator, we found that the efficiency of the drag reduction at Mach 0.5 was close to 74%. In addition, we showed that the change in the friction velocity scaled logarithmically with the spacing of the electrodes or the blowing sources. That's key because that's how we can design for scale, higher Mach number, lower Mach number, etc. With a 62% reduction in the viscous drag, we saw a reduction in all three velocity fluctuations that was proportional to the ratio of the change in the friction velocity, exactly what Klein found in 1969. We found a 35% decrease in the Reynolds stress, U via UW Reynolds stresses, and I pointed out a 66% reduction in the peak turbulence production. The reduction in the burst frequency, the turbulence production frequency, and magnitude scaled linearly with the reduction in viscous drag. And then the reduction in the three vorticity components included a 50% decrease in the control parameter, omega y. Now, the box at the bottom was a total surprise to us. This is not predicted by us. We thought the extent of the effect would scale maybe more like 2 boundary layer thicknesses if it were an outer scaling, or possibly something on the order of 500 wall units if it were inner wall scaling. But in fact, if we take the recovery time, which we said was about 4,000 T plus, if we assume a convective speed of 0.7 U infinity, which is fairly typical, then the equivalent streamwise distance to recover is 66 boundary layer thicknesses. Much longer than we ever expected. And believe me, we've done this calculation at least a dozen times, my colleague and I, Flynn Thomas, because we just couldn't believe it at the beginning. So what does that mean? In an application, you don't have to tile the whole surface with these actuators. You can have one here, you can wait, you can have one here, you can wait, you can have one here. You don't have to, and so the savings that you get in terms of the net drag reduction are even larger because you don't have to cover the whole surface. The next step for us is we are now in the planning stage of a flight test. This will be a full-scale flight test. It will be on aircraft that will fly at altitude over range from Mach 0.3 to Mach 0.8. And so a key thing in this is really the altitude effect, and that's one of the things we're looking to get. And so that is likely to happen in the next 2 years. So I also want to just list now, I promised to list the publications. Some of you want to take a camera and shoot an image of this so you could capture the publications. I've highlighted, not my name, I've highlighted all of my actual co-authors, which are Flynn Thomas, Alan Duong, and Andrew Myers. So I hope that this was interesting enough that you might follow up further, with these papers. Thank you very much.
You need to stay up here for a moment, and let me double check the order of things. We do have a few questions, but if you have other questions that you'd like to ask Dr. Cork, please use the QR code. All right, this was very interesting, even for a structural dynamicist.
Thank you.
So I appreciate that very much. On behalf of AIAA and the Honors and Awards Committee, it's my privilege to present you with the 2026 Dryden Lectureship in Research Certificate and Medal. So let's come over here.
Okay.
So I'm going to do this. Probably, if we can do this.
Okay. Wow.
Thank you. There you go.
It's heavy.
And here's your certificate.
Thank you.
All right, congratulations here. I'm going to shake your hand.
Okay.
And then please have a seat over here, and I'm going to get the
right.
questions that have been submitted.
All
Because
right.
we do have a couple of minutes here.
I think I got the timing pretty well.
Oh, yeah, it was great. We're about quarter after, so this will work out well. Now, you did share with us that flight test is next, and so that's exciting. It says here in this question, do you plan to complete any further wind tunnel testing prior to the flight test as risk reduction for new effects from curvature or PGs?
Yes. So the test article for the flight test will not be will be a separate element that is, let's say, on an appendage of the aircraft, and it's designed so that it will fit into our Mach 0.6 tunnel. So we will do a ground test with it before it actually does the flight test. So that's our way of reducing, uncertainties.
Okay, now this is a completely different direction question, but it says, as a first order estimate, how much electrical power do you think is required to operate this system on an aircraft scale?
So the nominal amount is, again, 14 milliwatts per square meter. So you can just imagine tiling that on a surface, and that's how you would calculate, what would be the power. But understanding that square meter will buy much more drag reduction power than the power you put in. So, but the nominal number is 14 milliwatts per square meter.
All right, let's see. It says, it seemed, and this was early in the talk, that riblets and spanwise oscillation are really opposite approaches to reducing surface friction. From what you've learned or your intuition, can you talk about that a little bit?
Yeah, so I don't think riblets work on the same physical principle of what we did, although oscillating wall does. An oscillating wall, if the frequency of the oscillating wall is sufficiently high, it produces a quasi-steady blowing. And that effect is equivalent to what we did. So as I said, the oscillating wall pointed to the physics. It's just not practical. The riblets are a totally different mechanism. And I don't know that there's actually a consensus of what the mechanism is for a riblet. One of the things is a scale. So the scales of riblets are fraction of the spacing between the streak structures, okay? Whereas in our case, our spacing of the blowing is on the order of 10 to 50 streak structures. So even the scale of what we do is much larger than that of the scale of a riblet.
This question says, did you investigate whether the vortex reduction from the electrodes also results in a reduction of lift generation in the airfoil?
We did not. We did not measure lift or drag on the airfoil. We only measured drag on that floating platen. Here's a consideration, though. Consideration is when we lower the viscous drag, then there's a greater chance of flow separation. However, in one plot, which I didn't emphasize, that you can actually overforce these actuators in which you actually increase the drag, which would be better in the case of a flow separation. So we've imagined that you could have these near the trailing edge of an airfoil and get viscous drag reduction when you wanted, or else added drag that would be important in the case of, let's say, a steep flap condition.
Now, is that also related? This question asks you to comment on the effects of the actuation frequency.
That's a good question. So the actuation frequency in our case only controls what the power level is of the actuator. So we have two ways of controlling the power. We can either control it with the DC voltage, or we can control it for fixed DC voltage by the actuator frequency. The real root of this should be, though, that the actuator frequency that we chose is not related to any known frequencies of the turbulence production process, meaning it doesn't relate to the large-scale passage frequency, and it doesn't relate to the burst frequency. So we've particularly chosen frequencies that are well outside the range of something that might interact with the unsteady process.
Okay, thank you. We have a couple of questions. The first one is about speed increases. And does that really affect the spacing, or will that affect the spacing of the electrodes? In other words, does that need to decrease, or is there a practical limit about the spacing?
That's a very good question. We've only, the largest amount of drag reduction that we've done is 80%. And that was with a spacing that corresponded to about 6 streak structures. The question goes, can we go lower? We just never tried it. We don't know where the limit is. One question we always get asked is the boundary layer relaminarizing? The answer is no. The drag reduction we get is nowhere near what it would be if the boundary layer was laminar.
Okay. And another one says, how does this work for extremely high Reynolds numbers?
It all scales with RE tau. So and it all scales based on the mean properties of the boundary layer. So higher Reynolds numbers, the scaling will hold up. In my opinion, I don't see that. Having the data that we received, from the experiment from the group from China, we were able to verify the scaling with Reynolds number based on the shear, which RA tau, which is really the appropriate Reynolds number. So far, at least as we can tell, the scaling with Reynolds number is known.
And this one asks if there have been or are there any efforts or future plans to look at this computationally?
Well, the initial work of Hussein, that was a simulation. Now, that was a simulation in a turbulent channel flow, and they simulated the span-wise blowing by introducing large streamwise vortices. Okay, that's kind of the extent. We would love to have simulation done with this. What I would suggest to do, if you were to do that, is not to try to simulate the plasma actuator, but rather just simulate span-wise blowing. And we did have a partner at one time in the very early work that was doing this, but they didn't carry it far enough. We might do it someday, but right now our focus is on the next step.
Okay. And we have a couple of other very specific questions, but I think that they would be best talked about one-on-one.
Okay.
And we do have, we're drawing to the end of our time. So I think let's thank Dr. Cork again.
Thank you very much.
Thank you. And 1 second, let me see if I have a final note I'm supposed to announce for you. So we hope you enjoyed today's lecture, and please enjoy the rest of the week at SciTech.